So I'm very happy to introduce Mike from Entrust. So Mike is participating to a lot of discussion about post-quantum and typically some that are in IETF. And it's an expert in computer science, crypto, and everything that we like within global platforms. So thanks a lot, Mike, for being with us today and taking some time to share your knowledge. And what I suggest is to leave you the room so you will be able to potentially finish your introduction if the mine was too short, but at least to start your talk. Thanks, Mike.
Sure, thank you.
You
I
may
recognize.
share your screen, Mike.
Excellent. That's helpful. Yeah. Good afternoon. Good morning. I recognize a few names in here that I are familiar, but
Yeah,
most
I
of you
assume,
I
yes.
don't know. Some. Not very many. This is a different
No?
audience, different group.
Yes.
Yeah, no, excellent. Yeah, so my day job is a application security architect. So I live within R&D. I'm a developer. I review our products for secure coding and secure architecture. I'm ethical hacker or pen tester as my day job. And then on the side, I do cryptography research, and I'm very heavily involved in all things post-quantum, mostly related to PKI, but I do touch other types of uses of public key crypto. I do some work on key attestation. I do some work on TLS, various types of crypto things. So I currently have one IETF RFC under my belt, and I have 12 more coming down the pipeline. So I spend a lot of hours per week. I'm also on the IETF Security Review Board. So yeah, so I'm heavily involved in all things crypto with internet. So let me see if I can get this screen share to work. I'm also a very comfortable presenter, so I'm okay to take questions live. You don't need to save them to the end. Where is the share? Is that successful?
Yes, we're able to see your screen, Mike.
Perfect. Okay, so I'm going to talk today about hybrid PKI hierarchies, which is a very specific topic. I can make this sharing bar go away. I guess it makes itself go away. Okay, yeah. So I mean, I could have chosen a wide range of topics to talk about here, but I'm going to focus in on hybrids. How do you build PKIs where you're using the old crypto and the new crypto together for either backwards compatibility benefit or for security benefit? But I'm happy to take questions on broader topics also. So just to set the scene here to get your brains into the right place where I want your brains to be, let's think about all of the ways that X509 certificates are used across technology in general. And it's quite broad. And so I want you to think about the core uses of X509. And I think everyone immediately, the most obvious one is TLS, HTTPS, but publicly trusted web certificates. That is the most common use of X509. But of course, there's this, and I'm going to phrase it as a very long tail of specialized uses of X509. As you get, so what makes web TLS sort of easy to work with is that the certificates are fairly short. They're limited to 1 year. You assume the web browsers are easy to patch. You know, Chrome and Firefox will update themselves. You assume the servers are fairly easy to patch, and if not, they'll have to come back for a new cert within a year anyway. So everything is fairly online and easy to get at. TLS is also really good at doing negotiations, cipher suite negotiation. So if you can just make a configuration change, and then suddenly the crypto used will be negotiated differently. So that's the really core case that's really easy. It's really well understood. But as we go to the right here, more into more specialized use cases, it becomes less clear that you can sort of just switch without any complications. like SMIME. SMIME is still a pretty common use of X509, but it's an encryption protocol. And you need to be able to open the emails you received. You may have received an email 10 years ago. You still need to be capable of opening it. So we have to think about key history. We have to think about sending emails today, the harvest now, decrypt later. So even SMIME is already a more complicated migration protocol. And you have things like PIV cards or e-passports. It's not entirely clear that you can just say on January 1st we're canceling any ID cards that are still RSA. Maybe you have some employees in the field who can't easily come into an office to get a new ID card by the deadline. Or e-passports are 10-year documents. We're 2024 today. That means there are passports being printed today that will still be valid in 2034. And there's nothing we can do to speed that up. They are 10-year documents. So again, as we go over 3GPP, SIM cards, Windows Smart Card login, you can use certificates for SSH. Those all get increasingly complicated in terms of migration implications. So I'm setting up my talk this way because as I present hybrid strategies, I want to make it clear that I'm not really talking about the core use cases. The core use cases will more or less take care of themselves. You can just decide, or maybe Cab Forum is going to decide for us, or maybe Etsy through the EI DAS specifications are going to decide for us. January 1st, 2030, we're switching to dilithium. And those are sort of easy. The core things, you can sort of just do that switch. So I want you to think more about the specialized things. When we're talking about hybrids, we're developing tools to handle the weird cases, the cases that aren't quite as clean. So it's a toolbox to handle special snowflake type situations rather than something we expect to be a core standard web mechanism. Okay. So what are the goals of these tools that we're developing? What are the design goals we're trying to achieve by designing these hybrid mechanisms? The first set of goals is the backwards compatibility goals. And I am sort of defining some new terms here because I think it's helpful for understanding. And so with backwards compatibility, some environments are lucky enough where you can patch everything. And you can be confident that by the switchover date, there will be no old things left. And by the switchover date, everything will understand dilithium. And if you can do that, that's great. You don't need backwards compatibility. But more often in the real world, there's some thing sitting somewhere in the corner that you can't patch, but it's very important. So we also can't turn it off. And so now we're in this world where you need new things to be able to still talk to old things, which is the whole problem of backwards compatibility. And so I'm going to define two types of backwards compatibility. The first is passive versus active. So in a passive backwards compatibility model, the new thing doesn't need to do anything. It doesn't need to do anything to downgrade itself. The downgrade is just automatic. Like both signatures are present on the data and the client gets to choose which one it wants to verify. That's a passive backwards compatibility. For those who are deeply familiar with X509, putting data in a non-critical extension is an example of passive. It's there, but the client, just the fail mode is just to ignore it. That's anything like that is going to be called passive. And then there's active. Active is where the upgraded peer can actively detect when it's talking to a legacy peer and can downgrade its own behavior. So TLS, cipher suite negotiation, is the perfect example of active backwards compatibility because there's a online negotiation phase that happens. So, all right, and depending on the complexity of your environment, depending on your migration needs, active might be perfect. If you're using certificates entirely for TLS, then active is great. If you're using it for things offline type things, you're encrypting files for someone, or you're encrypting a hard drive, or sort of these weird cases where you don't know if your peer is going to be post-quantum capable or not, then you might have to restrict yourself to the world of passive mechanisms, which is more tricky to do and less options for how to do it. The second set of goals is security. And so the first security goal of hybrid is we're calling hybrid security. Is the data strongly protected by both algorithms? And I want to consider here either what we call Q day, the day that a large quantum computer comes online and can break RSA, and suddenly any data that's protected only with RSA is done. Or the other case is that these new post-quantum algorithms, that dilithium or Sphinx Plus, that we find some critical CVE in them. And I think these are new enough, and I think, in my personal opinion, especially the lattice algorithms, are complicated enough that I think we're going to see 5 years of CVEs in them. I think people are not going to be able to implement these correctly on the first try. I think there's a lot of subtlety in implementing these correctly. So I think we should expect several years of CVEs in all the common standard libraries. So that brings you to hybrid security. Well, how do you do crypto so that if either algorithm fails, your data is still protected? And this gets into definitions like weak non-separability versus strong non-separability. And the academic security sort of professors, the academic researchers are busy investing time into trying to decide what it means to be weakly non-separable versus strongly non-separable and help us design better algorithms that are stronger. This also gets into the concept of whether the crypto operation that's protecting the infrastructure is itself hybrid secure. So your certificate or your TLS exchange could be hybrid secure, but what about the CA that issued it? What about the CRL that controls revocation in an EIDAS or a code signing case? What about the timestamp authority? What about the registration protocol? What about the SSH keys to log into the server? What about the firmware signing on the operating system? So the farther you get out, are all these layers also protected in a strong hybrid way? The second thing that we want to think about here for security goals is what I'm going to call discoverability and downgrade attack resistance, because those are sort of the two faces of the same coin. And the question there is, can you reliably detect when your peer supports post-quantum crypto? So if we're supporting one of these active or passive downgrade mechanisms, can you be tricked? Could an attacker sort of get in the middle of two upgraded peers, two post-quantum aware peers that would be capable of doing post-quantum, but somehow trick them into both thinking the other one is legacy and then downgrading to a weaker crypto that's easier to attack? And as we go through, we'll think about whether the mechanisms I'm presenting have this downgrade attack resistance property. So an example you can think of is, if you're going to continue issuing RSA certs to your infrastructure, sort of in parallel to your PQ, so that they can downgrade themselves, you could imagine putting a flag into that cert that says, by the way, a post-quantum version of me exists. And that would be a fairly reasonable way for a peer to detect, wait a minute, that guy's not legacy, because his cert says that he knows post-quantum. I'm going to refuse this legacy connection, give me his post-quantum version instead. And there's a closely related problem here of not just is my peer post-quantum, but is this piece of data post-quantum? So if I get a firmware object, if I get a code binary, if I'm launching Firefox.exe and there's only one signature on it and it's an RSA signature, is that the way that data was intended? Was it signed only with RSA, or was it signed with two algorithms and an attacker removed one? And is there a good way for the verifier to check whether it was intended to be one signature or whether it was intended to be multiple? Okay, so those are the properties, the backwards compatibility, passive active, and the hybrid security and the downgrade attack resistance are sort of four separate properties we're going to use to evaluate these schemes as we go through. So what's in the toolbox? Here's the certificate types that I'm going to talk about. The first is what has the marketing name Icera Catalyst, or subject alternative public key info. This is standardized in the ITU 2019 version of X509. So this is an existing mechanism. We'll get into the details. It's a non-critical extension to carry the second key. We'll get into a proposal called Chameleon, which is sort of a redo of the alt public key proposal with some different properties. Of course, there's multiple certificates. You can just start issuing dilithium off a brand new PKI completely independently from your RSAs. Multiple certificates with the related certificate descriptor. So that's that cross link that says a PQ version of me exists. And then finally, composites. Composites is where you really strongly use both algorithms together. So we're going to go through these one by one. And I actually don't have a clock showing. Oh, I see it. I found the clock. Yeah, I can watch my own time. How long does this go? Do you want to reserve 15 for questions?
Yes, 10:50 for questions. So
Perfect. I can do that. Okay, this slide I'll leave in just for reference after the fact. These are the standardization progress of all these things. I'll leave it in if people want to review it later. I will note that the top one was standardized by ITU. The bottom one, composite, is adopted by IETF, so it will become an RFC, but isn't an RFC yet. And the ones in the middle are in some in-between state of adoption. Okay, so the first one, this Icera Catalyst, or X509 2019 hybrid, or alt public key, whatever it carries a bunch of different names. Oops. The core idea here is that you take your certificate remains largely the way it is now. The subject public key stays RSA. The signature on the certificate stays RSA. But you hide, or you add an MLDSA. I'm going to use MLDSA, the new NIST names. If you're familiar with that as dilithium, that's the same thing. You can hide an MLDSA public key in a non-critical extension. And you can also hide a second signature on the certificate, a second signature from the CA. You can also hide it in a non-critical extension. And they're non-critical to get that passive backwards compatibility. If the legacy client doesn't recognize that extension because it's marked non-critical, it's allowed to skip it, and that's okay. So this is the core idea here. There's one little hiccup, which if you're very familiar with X509, you'll know that there's a signature algorithm field, both inside and outside the signed content. And so in order to validate these certificates properly, you have to actually your software has to modify the TBS certificate to blank out that field, to make that field empty, and then you can verify the signature. And the reason there is because in theory, the CA that creates the inner signature, the post-quantum extension signature, may not know yet what algorithm is going to be used to do the outer signature. They could, in theory, be decoupled. So you sign over an empty signature algorithm and then modify it later, which is sort of weird and it's tricky. It's tricky to get right. And within our IETF hackathon group, I think we had 5 people try implementing this draft over a weekend and then make sure we could interop. And we interoped perfectly because all of us got this wrong. All of us forgot to remove this before verifying. So this is a little landmine that makes this thing actually pretty hard to implement correctly, unless you really know what you're doing. Okay, so how do you deploy it? So the obvious way to deploy a catalyst is you just do catalyst all the way up. Whoops, that's a typo. The one on the far right should be end entity certificate. Your end entity is a catalyst, and the issuing CA is a catalyst, and the root CA is a catalyst, and clients can choose to use either key or both keys all the way up the chain at their choice. And this however has a few drawbacks to it. The first is that it's a new root certificate. So if you're in a world where if one of the reasons that your PKI is specialized is because you can't easily patch things, Or maybe you can patch the firmware of your devices, but you can't update the trust stores. I know that's a common design for embedded systems. For security reasons, the firmware, secure boot root stores are actually embedded in ROM, and they cannot be changed, and that's done on purpose for security reasons. So if you're in an environment like that where you cannot update trust stores, then having to make a new root certificate is actually a fairly big problem. The other issue with this is when you actually go to use this certificate. So I've got this cert, which has this beautiful backwards compatibility property, but how do I actually use it in a TLS handshake? Or how do I use it to sign a PDF? Which key do I use? Do I use the RSA key? Do I use the MLDSA key? Do I use both? What does it mean to use both? Can I put two signatures into a TLS handshake? How do I negotiate that? Do we need new extensions in the TLS client hello to be able to negotiate this? I'm actually doing some great work jointly with Wells Fargo and Wolf SSL. We're playing with this in the Wells Fargo lab, trying to figure out what's the easiest way. And we do have to modify TLS to support this. You can't do it out of the box. So it's really not clear how you actually use it. So I've given this thing a question mark for passive backwards compatibility. Like it really should have a check mark for passive backwards compatibility. That's the whole point. That's why it was designed this way. But because of this question of how do you actually use it at runtime, I'm giving it a question mark. It's actually not as passively backwards compatible as you think it should be. I'm also giving it a question mark for hybrid security. This could be hybrid secure if your clients are really strict about validating both signatures all the way up the PKI chain. But there's no guarantee of that. That comes down to implementing the client properly, and also legacy clients won't. That's the whole point. So as a sender, as a signer, as a CA, as a IT administrator, you don't actually know whether your clients are validating just the outer RSA or also validating the inner PQ. There's no way to control that. That's by design because of the non-critical extension. So again, I'm giving that a question mark. It's possible, but it's not. It's hard to audit and it's hard to control through policy. Okay, so there's a slightly less obvious way to deploy this, which solves one of the problems, which is you could start with a composite, or apologies, you could start with a Catalyst issuing CA off of your existing RSA root CA. So don't change the root, just start the hybrids at the issuing CA layer. Again, that should be end entity on the right. And so that solves the problem of immutable trust stores, but it does nothing to solve the other problem. The how do you actually use this at runtime problem doesn't get it any easier. So this actually, and now also because it's rooted in an RSA only root, it definitely does not have hybrid security. There's now no way to you can't even build a verifier that's smart enough to treat this as with hybrid security. So it gets a big red X there. So this sort of deploying it like this might look attractive, but really there's no advantage. It doesn't solve the hard problem and it weakens your security. So this is really not worth doing. There's one even less obvious way to deploy this, which is you could have parallel RSA and PQ CAs. So the root CA and the issuing CA independently on RSA and PQ, and then you somehow sort of cross-sign that extension in some cross-sign-y sort of way. And you could imagine doing this, and actually you get your hybrid security back, and you still sort of get your passive backwards compatibility back, and the original RSA CA cert, you don't need to touch it. But I think implementing this is actually going to be more tricky than it looks on the surface. I think actually writing code for this is going to be, you'll hit all sorts of weird edge cases. Like, what do you put? You're still in the end entity cert, you're only allowed one issuer DN. So do those two issuing CAs need to have the same DN? Is that allowed? What do you do for CRLs? What do you do for AA extensions? I think like this sort of looks clever, but I think in practice this is going to be harder to do than you think. So also I would not recommend this. So in summary of the Catalyst approach, this is really the obvious way to put two keys into a single certificate. Is we'll just put the second one in an extension. Currently, this is the only standardized hybrid certificate mechanism, although as of May 1st, the composite, which we'll get to at the end, was adopted by the IETF. So that composite will be an RFC. It's coming down the pipeline, but it's still true that as of today, this is the only actual standardized way. But the big footnote here that when you actually try to use a certificate like this, it raises more questions than answers about what you actually do with it. Do you use the primary or the alternate or both? I'll pause quickly for questions here if anyone wants to jump in before we go on to our next mechanism.
Is there any question? I don't think there is a question on the chat, Mike.
Okay. Then I'll keep
But
going and maybe I'll
voilà,
speed
keep
up a bit.
going. And if you
Voilà.
have any question, guys, use the chat so I can raise the hand for Mike.
Perfect. And I'll try and speed up to fit in the next 15 minutes. So Chameleon is really those of us who were, so I was on the original authors group in 2019, 2018 for Catalyst. And so the authors group has sort of rethought this in the 6 years since and thought, actually, here's how we should have done it. Should have done Catalyst, and this solves some of the problems with it. So Chameleon changes its color, it changes its shape depending on who's looking. And the idea is basically we're doing a diff. We're going to treat the RSA cert and the dilithium cert as two separate certificates. We're going to take a difference between them. We're going to take a diff, and then we're going to encode the diff into an extension. And so the serial number will be different, the subject public key will be different, the signature will be different, but a lot of things are the same. The subject DN is the same, the issuer is the same, a lot of the SANs will be the same. So you don't need to encode the things that are the same, you just need to encode the differences. And this allows, basically it's a compression. It allows you to compress two certificates together to look like one certificate. And this has, it behaves largely the same way as Catalyst, but it has a few advantages in that it solves the do I use one or do I use the other or do I use both problem. Because there is no other and there is no both. When you actually go to use this, you have a single key certificate, period. If you're using the base certificate, then clearly you're using MLDSA. If you're using the Delta certificate, then clearly you're using RSA. There's no ambiguity there. Again, I'm going to try and speed up a bit. So there is some implementation complexity. Reconstructing the Delta certificate properly is straightforward. That one's fine. One of the peers needs to do the reconstruction, either the client or the server, but not both. So there's a bit of who's going to do it. But once you do the reconstruction, once you extract the Delta certificate, then you just have two regular certs and everything goes as normal. We've solved the runtime complexity problem. I'm going to skip this slide in the interest of time. This is the technical details of how this works. So how do you deploy it? So it's now designed in this mode where you have two unrelated PKIs, and then the cross-signing works in a really straightforward way. Because now you're allowed to specify a different issuer DN, you're allowed to specify a different AIA, a different CRLDP, so that now you can cross-link really cleanly. Yeah. So here I'm giving an actual full check mark for passive backwards compatibility. The hybrid security is still possible, but up to the details of the verifier, but passive backwards compatibility is cleaner here. You can also do it the other way. So on the last slide, I showed RSA as the outer signature and MLDSA as the inner. You can, of course, do it the other way. So as you sort of go through your migration journey, you may want to start with RSA being the default sort of backwards compatible version, but at some point you may get more of your clients can do MLDSA than RSA, and you may want to flip that. So this sort of upgrades nicely. At some point you flip it, and then at some point you just drop the RSA entirely. So it's got a nice sort of migrate out story also. So summary of Chameleon, it's our second try at the hybrid extensions idea. It's still using an extension, but it uses it to encode a difference rather than to encode directly a public key. It's essentially a compression or a zipping to nest two related certificates inside each other for easier transport and management. And by nesting them like that, you get some security that they are related because the inner one has been signed over by the outer one. So there is cryptographic binding, which is good. But it also allows them to be separated back out into two independent single algorithm certs for straightforward use. So we really like Chameleon. We think that anyone who's looking at using Catalyst should consider whether Chameleon is a better fit, but it is less mature in the standards track. All right, multiple certs is my next topic, unless there are questions on Chameleon. None, we'll keep going. So multiple certificates is the proposal that just says, well, really don't do anything new, just get multiple certs. Just you have your RSA PKI, just stand up a new MLDSA PKI and provision all your servers with 2 certs. That's it, simple. And it is simple. And in a lot of cases, this is great. In a lot of cases, this will work perfectly well. For web PKI, I think this is probably the default answer. When we did the RSA to elliptic curve migration, we built out all these mechanisms so that servers can have multiple certificates and TLS can negotiate, and it's all, the server can then choose which cert to use based on the client hellos. So we have a lot of the infrastructure for this already. So in a lot of cases, this is a good fit, but it's not a good fit everywhere. It only works when you have active backwards compatibility. So when you have something like TLS that can actively do that downgrade negotiation, if you don't have that, then this is a really bad fit. So like SMIME email, if I'm trying to send an email to someone, I'm trying to encrypt an email for them, and I only have one of their certs, I mean, I have to choose to pick. And if I see that they have 2 certificates in the directory, which one should I use? And maybe their Outlook on their laptop can access both keys, but maybe the Outlook on their phone only has one of them. Like this really introduces a lot more complexity in some of those sort of, again, as you go into the more specialized use cases, you'll find that this hits more and more edge cases in deployment. You still have the problem of how do you actually use this at runtime? Do you use one or do you use the other or do you use both? So like if you're signing an SMIME email or you're signing a firmware image, you have to grapple with that problem of, how do I actually combine them? You have the related hybrid security problem, which is when you write the verifier, is the verifier expecting 2 signatures? How do you prevent downgrade attacks? If these certs are really unrelated, how do you know if one of them has just been removed by an attacker in transit? So downgrade attack resistance becomes a pretty hard problem. So if you really want that strong security, it's much harder to get it here. Not impossible. So I've given it a question mark for hybrid security. It's not impossible to get hybrid security, but it's much trickier and there's a lot more edge cases you need to consider. I did do a review of which protocols have passive or active backwards compatibility mechanisms that would be compatible with this. CMS, which underpins a lot of PKI and underpins SMIME, does. That's great. OpenPGP does. XML DSIG, I think the answer is no. TLS, obviously the answer is yes. JWT and CWT, I think the answer is maybe. Those protocols do support multiple signer infos, but I don't think very many clients and libraries actually implement the signatures array. Most of them just implement signature as a single object. So on multiple certs will work in some cases. It will definitely work for TLS. It will definitely work for CMS. It's definitely work for OpenPGP, but it's unclear how well it'll work, again, as you get more into those specialized uses. Hybrid security. So the last slide was looking for backwards compatibility. This is hybrid security. CMS actually does. CMS published a draft called Multiple Signatures in CMS back in 2010, and it allows you to cross-link 2 signatures. So actually CMS does allow you to get hybrid security here. Every other protocol I looked at does not. There's no way to get multiple certs to do hybrid security in any of the other protocols that I work with. So let's add that then. If we want the hybrid security, let's make a new mechanism. Let's register a new extension that gives you the hybrid security. And so this is the draft that we're working at. I'm sorry, there's a draft that already exists, which was published by the NSA called Cert Binding for Multi-Auth. And it defines this extension where a related certificate is an octet string, which is a hash of the related cert. So it just says somewhere in the world is a certificate that's related to me, and here is its hash, which is okay. If you already have both certs, you can confirm that they're related. But if you don't have both certs, it's hard to find the other one just from its cert hash. And you don't know whether it's related because maybe you changed DNs or maybe you changed departments within the company and you got a new cert, or if they're related because one is legacy and one is post-quantum. I think the NSA had something very specific in mind when they wanted this draft published. I don't think it fully solves the problem. Whoops, that was the wrong button. So we've published a new draft, which is not adopted yet, which is a broader version of this. It's the related certificate descriptor extension. And here you can put a URL or sort of any other type of name. And so here you can actually point and say a post-quantum version of me exists and here's its URL. So this really allows that cross-linking. We think it's great, but it hasn't been adopted yet. And so you can set up a PKI like this, where you have two unrelated chains, and then the end entity certs are cross-linked via this related certificate descriptor. And you can do the cross-link in one direction or the other direction or both directions. So this gives you that nice passive backwards compatibility. It could give you hybrid security, and it gives you discovery and downgrade protection. So we really like this. We're really hoping it gets adopted by the IETF. We think it's simple and straightforward. So yeah, in summary of multiple certs, hybrid security is generally not well supported by the protocols that you would have to use certs with. You get no help in hybrid security from the certificate itself. You would need that to come from the protocol. Backwards compatibility is actually fairly well supported. That's a good story because we get to piggyback on all the mechanisms invented for the elliptic curve migration. And the discovery problem does have some proposed solutions via cross-referencing, but they're not yet standardized. Again, pause for questions.
Is there any question? I have one.
Please, yes.
Yeah, so I was expecting the end of your presentation, Mike, because every solution looks good, at least to the migration. But what you will recommend if you need to be ready by 2030?
It's hard to make a single recommendation. So that's I started at the beginning with the long tail of
I know
use
that,
cases.
so
I
I have added the
toolbox.
year to be ready.
Yeah.
2030. You need to have everything ready. Means that the HSM or whatever, the infrastructure, everything is ready. So some retro. I think based on the maturity of some solution, you may say that this one is a good one, but it will be ready after. Or I was just trying to have one filter, which is the time of delivery.
One filter at a time. So if you can afford to wait, 2030 is still 6 years away. If you can afford to wait, then presumably you can afford to patch everything. Between now and 2030, you'll be able to patch everything. You'll be able to reissue ID cards to all your employees. Like the best thing is the hard cutover. You just say on January 1st, 2030, RSA will no longer be accepted. Sort of treat it like a Y2K. That's easiest. That's the most straightforward. And if you have lots of time, that's always the best strategy. Or if all your protocols, if you're only using certs for TLS, then you sort of do a soft flag day, a soft cutover where all new, things will only be receiving new certificates with dilithium, but will still allow downgrade to RSA. Like if you can do that, you should do that. That's going to be easiest and avoid this whole hybrid thing entirely.
But
But
typically, so passport with 10 years will be used by 2021, 2031, 32, 33. IoT object will be also used, and the one that are released today, right? So I think hybrid will be needed to be able to have at least 2, 3, 4, 5 years, even though the deadline will be 2030, but between 2030, 2035, potentially we need to have to accept the two. One solution may be to have two infrastructure, I assume, but if we want to have the hybrid one.
So I really like composite, which I haven't got to yet.
So go on the composite. Sorry, maybe
I should go on, do the last one. So I like composite. I think of the backwards compatibility. So composite does not give you backwards compatibility; it gives you security. Of the backwards compatibility things, I think it really depends why your problem is hard. Whether you're using the Icera catalyst or the chameleon or the multi-cert or the multi-cert related certificate extension. I think which one of those is better really depends on the details of your problem, the details of your migration problem. Like for ePassport, I actually think the Catalyst certificates is actually the best fit for ePassport due to really technical reasons about how the chips in the passport interact with the issuing stations. There's some details there that I think actually make Catalyst the best fit. But for other cases, like maybe ID badges in a company, multi-cert with related certs is the best option, unless your chip can only hold one certificate and one private key, in which case that option is out. Like you really, really fast get into details, right? Okay, let's do composite, and then there will be a few minutes at the end for questions. So composite is it is not a backwards compatibility mechanism. It is a security mechanism. It gives you hybrid security. And the core idea here is that rather than use ID MLDSA 44, so rather than make certs that say I'm an MLDSA cert, we're going to create certs that say I am an MLDSA and RSA cert. And so your public key is actually, you'll have a key which inside of it has two keys, but we're going to think of it as one key, and that one key has type MLDSA 44, RSA 2048, PSS SHA-256. That is a single public key. It creates a single signature. Yes, there are two separate signatures buried inside of it, but that's just details for the crypto library to sort out. For all intents and purposes, we're going to that is one algorithm. And this has some nice properties. If you have a FIPS certified RSA PSS implementation, then you automatically have a FIPS certified MLDSA 44 RSA PSS implementation without needing to do a new FIPS certification. So the FIPS has made that clear, that NIST has made that clear, that combining things in this way, you get to keep the properties of the strongest algorithm. Even if the MLDSA is totally broken, the fact that it's combined in this strong way, you still get to claim full security from the RSA. It does not receive any backwards compatibility, so you may need to couple it with one of the backwards compatibility mechanisms we've already mentioned. But it does have something we call protocol backwards compatibility, which means that if you just start creating certs with this new composite OID, as long as the crypto library at the other end knows how to read that algorithm, you don't need to make any changes to the protocol. So you may need to add some new cipher suites to TLS, but you don't need to add new negotiation mechanisms. For CMS, you don't need to add anything new. It's still one certificate. If the chip in your card only supports one certificate, one private key, this is still just one certificate, one private key. There's sort of absolutely nothing weird. There's no extensions. There's no new processing logic. It's just simply a new algorithm. And algorithms is where we tend to have the most crypto agility. Almost every crypto library can support adding new algorithms. So we're going to hide all the complexity in a new algorithm. Encryption works largely the same way. And the bonus here is that this is the only thing I've mentioned so far that works for encryption. Everything else I've mentioned works for signature type certs, but none of the other mechanisms work well for encryption type certs, but composite does. So composite, you can register a composite encryption algorithm with ML-Chem and RSA, just the same way you can register a composite signature algorithm. And this allows you to encrypt the data in an AND mode. So the attacker would have to break both algorithms in order to extract the data. There's a question here about whether we want to support RSA combinations, and this is a debate I've been arguing furiously at the IETF by saying that we have many customers who never actually implemented elliptic curve. Many of the big, especially in the financial sector, things tend to be really RSA only. And so I'm fighting really hard at IETF. The browser guys are like, but elliptic curve's been around for 20 years. What do you mean you don't have it? So this is a big raging debate whether we need the RSA plus ML chems as a stepping stone or not. So yeah, I've got a few more slides, but that's sort of a logical end if we have questions, and if we don't have questions, I have a
you
few
start to have
more.
questions, Mike. So
Excellent, let's do them.
Chris, you want to ask the question, or Mike, or I'm reading. I don't know if Chris.
I don't have the chat up, so if you could read it, that would be good.
Yeah, by all means. Thank you, Mike. This is superb stuff. I was just wondering whether any particular intermediate solutions can provide that best provide forward compatibility. So, is it possible to prepare the ground most effectively for versions of libraries and implementations at either end, which give for an easy time? I'm not sure if that's a reasonable question to ask, but that's nevertheless. Yeah, thanks for the great talk, by the way.
Yeah, you're welcome. Yeah, what do you do as a preparatory step if you're not quite ready to implement these? But yeah, I mean, the obvious answer is just make sure your things are patchable. Make sure you're thinking of, if your clients don't have the ability to update root stores, maybe you should, as preparatory work, think about adding a mechanism to be able to securely update root stores or securely deprecate algorithms or securely roll over keys. If your clients won't come back and ask for a new key until their certificate expires, maybe you want to think about a way to force them to phone home early. Like, I think those sort of crypto agility questions, like sort of in preparation for being able to do a lot of this, is make sure that your stuff is able to accept new crypto on the fly mid-cycle. I don't know if that's quite the answer you were looking for.
No, that's actually very helpful. Thank you.
Like and at the IETF, we get a lot of people have come up with these sort of weird, complicated hybrid crypto things. And someone comes to the mic and says, just figure out firmware patching. That's not my problem. And sits back down.
Mike, do you want to ask your question?
If you could read it, it's probably easier.
Okay. So my question is about.
Gio?
No, I can do it. My
Okay.
questions was about Catalyst and Composite for EMRTD. I assume that you can do anything that you want in the issuance side and with the document, so the EMRTD. And your biggest concern is that the verifier, so as a border,
Yes.
especially where Composite can address encryption.
Yes. So
and you have also a little support for keeping fighting on for RSA. That's from Mike.
Yes. Thank you. Now, sorry, I'll do the second question first. On the fighting for RSA, I'm losing the battle because I don't have any good Entrust customers who are willing to go public. And so I say, we have customers with complicated RSA migration, and the IETF says, great, who are they? And I say, I can't tell you. And that's the end of that, and it goes nowhere. So if it's important to you to have RSA-based migration mechanisms, and you're willing to make public statements at the IETF, that would be very, very helpful. So if you think you or your organization might be willing to go on public record for why you need RSA-based hybrid mechanisms, please email me. It would really, really help. I think I am going to lose that battle unless people are willing to go public. Okay, so the first question is asking about more detail about the EMRTDs, the e-passports. So the hard problem with e-passports actually isn't the chip to kiosk, it's the kiosk to chip. It's the BAC side. Because you can, generally speaking, patch the kiosks. And then if I show up with an old passport that does RSA, the kiosk says, okay. And if I show up with a new passport that does PQ, the kiosk says, okay. What's harder is if I have a upgraded kiosk and the kiosk has a post-quantum certificate, but the chip in the passport doesn't know how to read it. That's the hard part of that. And that's where I think Catalyst was a really good fit. The EMRT document, is CMS based, and so you can do multiple signer infos, and so that's where we think Catalyst is a really good fit, because the kiosk can present a Catalyst certificate, can sign the transaction twice using a second signer info. The question I don't know is whether chip implementations have like the ones out there today, currently out in the field, support multiple signer infos, because the ICAO specs don't use the multiple signer info functionality, so there isn't really a reason for people to have implemented it in the small code space. So that's a bit of a question, but assuming that it is, assuming the chips out there today can gracefully ignore a second signer info they don't recognize, then Catalyst really is, I think, the right answer for the BAC.
So,
side.
Mike, just to bring a finer point to that, I think you're addressing the BAC and the PACE, some call it PACE,
yeah.
where the chip is actively engaging with the passport. I'm speaking more about the passive authentication, where you have the public key directory that ICAO manages of all those signers, that you're basically just verifying the signature on the hashes of the data. So all of that's done off terminal. You basically read the SOD, which is a file full of hashes that has a signature on it. And that signature would need to be made in a way that could survive Q-Day. So I'm wondering if composite is the answer for that, as opposed to the other one.
This is not an aspect I have put thought into, so I don't want to say something dumb on a recording.
No, I don't want to ask a dumb question either.
No, it's an excellent question.
No, I mean
that sounds right.
In the ICAO community, that's the one we're most concerned about, honestly. Is
interesting.
If you lose the integrity of the SOD, the security object data, then you got a bigger problem.
Okay, so I mean, it really comes back to what are your goals?
Mm-hmm.
I mean, if you come all the way back to here and we ask, what are you trying to achieve? If hybrid security is the goal, if you say this data has to live for 15 years and we're not sure that we really trust MLDSA to still be a good algorithm in 2040, then composite is a really strong option there.
Okay, cool. Like everything here, it's a good place to start. We're not exactly ahead of the curve on here, I don't think. Thank you.
Yeah, it's EMRTDs is an interesting use case, because in some ways it's the poster child for we're producing stuff today that still has to be valid in 20 years. Yet, yeah, I think it's been a bit late in getting started on this.
Okay, thanks. So the intent of this call is to be short, Mike, and I suppose that many people will have some questions and we can stay all together 2 or 3 hours more. Nevertheless, there is a comment. It's not a comment, but we hope to receive your slides and to be able to share, because of course we have a lot of discussion. We are trying to have the new protocols based to be agile enough to support also post-quantum crypto that we are thinking about. And there is a question about, of course, certificate. Next week, we have a lot of discussion about that. So Sebastian from Oracle is asking, but I'm sure that you will send it to me and then I will share it to the community. Thanks a lot for your time, Mike. Really interesting. really 100% on some of our questions about how to migrate, when to migrate, some asking for my hybrid. So everything was on their talk. So thanks a lot. And again, for the audience that for your information, we easily reach 120 people connected today for your call, Mike. So thanks a lot for, yeah, definitely this is a strong topic in our community. And for the other global platform expert, yeah, we were close to 130, says Mike. So we are looking for a good presentation for the July/August. Certainly the August, last week of August, we will have a tech talk. Thanks a lot all, and really appreciate your participation, Mike.
Thank you for having me.
Thanks.
Thank you so much, Mike. Thanks, everyone.